So can everyone see my MATLAB screen? Yeah, okay, great. So if I throw this window in here, can you see this window as well?
Yep.
Yeah, okay. So as Joe was explaining earlier, the structure of your folder for the tutorials should look something like this. So just turn that off. So you should have 3 folders: data sets, libs, and tutorials. So in your data set, the only one you're going to need for this tutorial is LOL or natural speech, and preferably the CND format. We'll be working exclusively with subject 10 as well. Stimuli. So there was a stimulus file that was uploaded separately. The one we're going to use is the 64 Hertz version. That is actually contained in the tutorial file. So when you download the tutorial, you should have this datastim_64 Hertz file. So you can either leave it there and change the path to that file, or you can throw it into the stimulus folder here in datasets within LOL or natural speech. Okay, you'll also need some of these functions as well. So then in libraries, you'll have some basic utility functions just for analyzing CND data and doing some basic pre-processing. You'll need EEG Lab. You'll need MTRF Toolbox version 2. I don't think you'll need noise tools, if I remember correctly. So just make sure they're all downloaded and ready to go. The code will set the path to each of those, so you don't have to worry about doing too much setup to your environment. And then if you unzip the tutorial itself into this folder here in tutorials. So okay, I'm just going to put the chat here so I can keep an eye on it. Yeah, so I'll be going through each section of the tutorial with you guys, and we'll go at whatever pace we need to so that everybody can run the code and get it working on their machine. I also have Stephanie and Giorgia here with me to help out, so if you have any questions, throw them into the chat. I'll keep an eye on that, as will I. I don't see anything in the chat, so I'm going to assume that everybody is set up and ready to go. So with that, we'll get stuck into the TRF tutorial part 1. So basically what we're going to do first is we're just going to kind of walk through some of the basic steps in order to train a very simple linear encoding model using the speech envelope. We'll talk a little bit about the pre-processing and feature extraction side of things, but most of the stuff that's been left out is to do with actually generating the models themselves, training them, doing the cross-validation, testing them. The code that's used for doing all of the training and testing of the models is based on the MTRF toolbox. So if you are trying to figure out how to implement the different steps, you can open up, I'll just link it here in the chat. You can either open up the code in MATLAB itself, or I can link the GitHub here. Okay, so most of the functions you'll need are contained in this folder in the MTRF toolbox. So it'll just help when you're trying to figure out what parameters to put in where, etc. So, okay, so basically the first step is to kind of just set up our environment and ingest our data. So Stephanie kindly pointed out that you may have trouble running the code as is if you're a Mac user. I'm seeing that my screen is a little bit jumpy, so let me know if you can't hear me or see what I'm doing. My Wi-Fi looks like it's pretty good, but it can be a little bit dodgy at times. So basically the way I've kind of designed the code is so that it can be run in blocks. So instead of running the whole code start to finish, which won't work, of course, because there's snippets of code left out, so you'll just get errors. You can run each section either by clicking the run section button here, or on my machine, I can press Control Enter. I think it's different on a Mac. Stephanie, do you know what the command is to do that? Is it something like, is it?
It's Command Enter. I just figured that out by hovering over Run section, the Run section button on top.
Oh, great, yeah. Okay, so if you hover over that, it tells, oh, sorry, this one here. Yeah, Control Enter on Windows and Command Enter on Mac, great. Okay, so basically what we're doing here is we're just, I'll try and make as much space here so you can see what's happening. So we're just setting the path to the tutorial folder first. We're just adding a few important folders and libraries within that so that it knows where to find all of the functions and our data sets. Then we're loading in specifically subject 10 because they're a good subject. So their data is nice and clean. It's easy to demonstrate all of the different features that we'll be showing with their data. And we'll load in as well the stimuli at 64 Hertz. And you need to run EEG Lab as well beforehand just to be able to access some of their functions. So the first thing we'll do is some basic pre-processing of the data. Basically, we're just going to do some fairly modest filtering, bit of downsampling, interpolation, re-referencing. So for this, what we're going to do is we're going to high pass filter the data above 1 Hertz and low pass it between below 8 Hertz. I mean, this is might seem a little extreme for those of you who are used to maybe doing standard kind of ERP style analysis. But it's just to be able to, for demonstration purposes, get some really nice response functions so that you can see all of the dominant peaks in the right places. Typically, you know, you might, if your data is clean, you might want to include, you know, much higher frequencies in around the beta and low gamma range. So, you know, up to about 30 Hertz or so. But you know, the high pass is pretty good. I'm gonna have to turn this off as well. Okay. So we're going to use filters with an order of 3 Hertz. We typically tend to keep the order of the filters as low as possible, and the reason for that is because the higher the order, while you might think they're closer to a more effective or ideal type filter, they can introduce a lot of artifacts into your data. So, sorry, now this stuff is coming up from, I might move this over the other side so that stuff isn't popping into the window. How's that? Can you guys see everything okay? Yeah, okay. Keep the solutions away so you can't see them. Okay, so yeah, so we're just going to go with a third order filter here in this case because we have a good subject with good clean data. So we have this function as part of the CNSP utils that will get us the coefficients for the filter that we need. So if we just tell it what the high pass order is and the cutoff, it'll compute them automatically, and the sample rate of the data. And then we can put them into a really useful function called filtHD. Now, just before we start talking about the actual processing, I'll just mention a little bit about the data itself. So Giovanni already talked a bit about this in his talk. So this is what the EEG data looks like. So it's a structure with multiple fields containing information about the data type, the name of the system used to record the data. The trial position is just the order in which the data was recorded. FS is our sample rate, so the data was either sampled at 128 hertz or downsampled to 128 hertz at some point, probably downsampled. The data itself is contained within a cell array, and then we have our external channels that we might want to use for, say, re-referencing the data. And then we have a channel location structure that contains information about the spatial locations of the channels if we want to do topographies or anything like that. So the data itself, as I said, is contained within a cell array. So you've got, in this case, 20 cells. Each cell contains a matrix with 128 channels in the columns and some large number of samples in the rows. They're all slightly different in size because presumably, there was some manual process used for starting and stopping recording. But as far as I know, they're all about 3 minutes long. So basically, the participant in the experiment was listening to natural speech. They were just audiobooks. Jules Verne, I believe, was the audiobooks they were listening to. I can't remember which story exactly. It's either Old Man in the Sea or 20,000 Leagues, or 20,000 Leagues Under the Sea, or Journey to the Center of the Earth. So basically, we record the data in chunks of 3 minutes just to be able to give the participant a break so that they can relax and that they don't get too fatigued and start to mind wander and things like that. So that's the layout and the structure of the EEG data. Our stimuli have a kind of a similar setup. So our sample rate, as I mentioned, is lower. It's 64 hertz. So we'll have to either downsample the EEG data to match that or upsample the stimuli to match that. So it'll be easier to downsample our EEG data. And if we look at the stimuli itself, we've got more stimuli than EEG data. And the reason for that is because we've already extracted several different types of features from the speech. So in the first row, what you have is the envelope, which Liberty was explaining earlier. So that's just the kind of low frequency intensity of the signal over time. We've got a 16 channel spectrogram. We've got 19 different phonetic features. And then we have basically a vector of word onsets that indicates the amount of semantic dissimilarity between every word and the preceding words in that sentence. I know that's a lot to take in. I'll explain that a bit later when I get to it. But basically, what we've got here is a kind of a hierarchical representation of the speech signal so that we can look at how the brain was processing, kind of low-level acoustic features versus more rich spectrotemporal features versus phonetic level processing versus semantic processing. So that's the idea of the tutorial, is to get through a a forward encoding model that represents each of these different features. And once we've that done, then we'll get on to the backward decoding model stuff. So I'll go back to our code here. Is it large enough, by the way, the font? Can everybody see the code? Or do you want me to increase the size of the font? Okay, so, okay, thanks. So the EEG size doesn't match the stimuli for each trial. Is this because of a pre-post stimulus included? No, it's not to do with a pre or post stimulus stuff. Basically, the data would have been, like, recording of the EEG data would have started before the stimulus occurred, to make sure that we catch the onset of the stimulus. And then after the stimulus stops, recording stops. And, you know, if this is all done manually, there's going to be some arbitrary number of samples either side of your stimulus. So what we've done is using triggers, we've time locked where the start of the stimulus is. So all of the EEG is time locked to the beginning, but there might be a few kind of leftover samples at the end. So the EEG data should be larger than the stimulus. And so all we have to do then is, when we're processing the data, we'll just kind of truncate the end of the EEG to chop off any extra bits that we have. Okay, so yeah, so the first thing we're going to do, as I said, is we're going to filter our EEG data. Now, because as I explained here, the EEG data is contained in a cell array. Okay, so each matrix of data, each trial of data is in an individual cell. In order to filter the data, what you might do is, you know, create a for loop and iterate through each cell and apply your filtering channel by channel. But there's a really convenient way to do it in MATLAB using the cellFun function, where essentially we can ask it to process a number of cells simultaneously. And all we have to do is define what we want to happen, which is we want the filtHD function to run with these coefficients that we've defined on some variable x that we've defined here. And then x is going to be our EEG data. And we just have to indicate that the output won't be uniform. So for those of you who haven't used this before, it's a really convenient way to process your data if it's contained in a cell format. And because the CND format, which Giovanni was talking about earlier, always contains your trial data in a cell array, it's something that you'll see being used here quite a bit. So that will filter our data, essentially bandpass filter our data between 1 and 3 hertz. Or sorry, 1 and 8 hertz. We'll then do the same for the external channels. The next thing we'll do then is we will downsample our data to 64 hertz. So, of course, we do this after low pass filtering the data to make sure there isn't any aliasing occurring. So now we'll have both our EEG and our stimuli at 64 hertz, so that we can do a kind of a one-to-one mapping, sample by sample. So for downsampling, we're using this CND downsample function. Again, you know, it's just a very basic wrapper function that we made for you guys, so that if your data is in the CND format, you don't have to go unwrapping the structure to get the data itself. You can just throw it in here and you specify the new sample rate. It can tell what the original sample rate is because that's contained within the EEG structure itself. Then we'll interpolate some of the bad channels. So what I mean by that is we'll identify some of the channels that have either abnormally large or small standard deviation compared to the other channels or the mean of the other channels. And we'll then do a spline interpolation of the surrounding channels in order to get rid of those bad channels. So to do that, we have a function for you guys just called remove bad channels. For this one though, we do have to loop through the cells individually. So
question
after that then, yeah.
Question, does the remove bad channels get rid of channels that have pretty good data quality but a few artifacts in there? Or is it kind of correcting noisy channels because of impedances?
So what did you say first?
Like, does it get rid of channels that have artifacts periodically, or does it get rid of channels that maybe have poor impedance, that have poor signal quality throughout?
I would say it's more sensitive to channels that have more consistently ongoing noise, because it's looking at the standard deviation across. If I remember correctly, I can open the function here. If I remember correctly, I think it might look at the standard deviation across different segments of the data.
I could look into it offline as well.
Yeah, it might just be looking at the entire channel for that particular trial, but it's done anyway on a trial by trial basis. So
okay.
Yeah, so it's, you know, it's just a very simple way to kind of clean your data instead of actually trying to recover the signal by some more sophisticated method of, you know, removing the artifacts or the noise. We're just going to say, well, look, you know, because of the, you know, autocorrelation between channels, with the EEG, because of volume conduction, we can just, you know, basically infer what the signal should look like from the surrounding good channels. So after there's also, you know, a good way that you can kind of check to make sure that you're not throwing out good data is to then look at maybe the correlation or the, you know, mean squared error between your new channel and the old one that you kicked out. And if it's very high, you know, if the similarity is very high, then you're probably getting rid of good data. So you can also kind of build in a little check there. Then after that, we are going to re-reference the data to the mastoid channels. So they're the channels that we record just behind the ears. We typically do this for auditory experiments just because we tend to get a nice response around the top of the head if we do that. We then normalize the EEG data just by the standard deviation. Again, using the cell function, just it makes it a lot easier. And then at the very end, then we crop the EEG to match the stim length. So as someone was asking there in the chat, we ensure before we do our modeling that all the stimuli and the EEG are the exact same length. So first you have to match the sample rate. Once the sample rate is the same and you're sure that the onset of both signals is the exact same, you can truncate whatever is left over before the analysis. So has everybody successfully ingested the data and set up their environment? If anyone hasn't, maybe just, you know, throw whatever errors you're getting into the chat there. Once you have that done, you can then run the data pre-processing block. So I'm running mine here now. So it shouldn't take too long. Again, it's just one subject. So you're going through 20 trials of 3 minutes. So it's about an hour of data.
Mick, are you able to see the chat? There's a question that I think you might
Oh,
be able
yeah.
to answer.
Thanks. That's a great question, actually. So yes and no. If you're doing something like, you know, using your model to predict the neural response to new data, you know, or if you're doing a decoding model, so mapping backwards, you tend to get pretty much the same results no matter what referencing technique you use. However, for more qualitative analyses, if you're trying to visualize response functions, you know, components, neural components at different time lags and things like that, then the referencing technique will have quite an effect on what you'll see. Not only, you know, will those peaks and troughs become larger or smaller at different time points, but you know, you could see complete inversions of those components depending on where you took your reference. So that's why, you know, if we're going to record up the top of the head, it's nice to take a reference right down here to try and emphasize those signals in the auditory cortex. Similarly, you know, if we were doing a visual experiment and recording from the occipital cortex, we might take a reference towards the front of the head. So, you know, in general, you'll choose it based on, you know, the modality you're working with, type of stimuli, what you're trying to do. But it's, you know, it doesn't change the data fundamentally. You know, if something's happening in the brain, it's still going to be there after you re-reference it. Okay, so I have run the pre-processing block here. I don't know why this is really slow. I guess I'm running a lot of processes here at the same time. Maybe I'll just close Chrome. Try and speed things up a bit. So you can see it identified 5 channels that were bad. We've got 128 channels to work with, so throwing away 5 channels is nothing. That's fine. Okay, so we can deal with that. I mean, the kind of rule of thumb you'd normally work with is you know, anything more than 10% of your channels, and you'd want to maybe rethink either, is it a good data set, or is the criteria you're using to identify bad channels, is it a little is it not strict enough or too strict? So I see somebody got an error, unable to resolve the name of design high pass. I wonder, did that come out of, was that when they ran line 80 from the fill HD? Oh, in get high pass filter. Okay. Interesting. So I wonder, are you missing an essential toolbox in MATLAB in order to run that line 33 F design? To download, yeah. So you'll need the signal processing toolbox. Yeah, thanks for that, David. Yeah, so if you could download the signal processing toolbox, that should help. And I'll just keep going then in the meantime, and you can try and catch up then when you have that. Okay, so we removed about 4 or 5 channels in every trial, and you can see that they were the same channels each time, which kind of tells us, okay, they're most likely bad channels, and everything else worked fine. So the next thing, before we actually start building our model, I know we already have all the different stimulus features we need in the stim data variable, but I'm just going to demonstrate here how you can very easily compute the envelope of the speech signal using a simple function that we provide in the MTRF toolbox. So if you run section B1, oh, this is really slow. Okay, so if you run section B1, it should throw you up this figure. So what we have here is, so there's an audio file, an actual real audio file in the MTRF, the TRF tutorial folder, and it's just 5 seconds of audio. And so in blue here, what we've plotted is the original audio that the participant actually heard. So you can see it's still at 44.1 kilohertz. There's a lot of information there. And what we want to do is extract the kind of low frequency power of the signal, the envelope, at 64 hertz. So we can do that using this function MTRF envelope. So we just input our audio, the sample rate we want to come down to, and I'll actually have to check what those arguments represent. I can't remember. Okay, the size of our window and the compression we want to apply to the signal. So basically, if the window is at 1, it's just going to average over the amount of samples it needs to average to get down to that sample rate. If it's any larger than 1, it'll increase that window and it'll apply some additional kind of smoothing or low pass filtering. And then the last argument is the amount of compression we want to do. So we didn't apply any compression here, we just set it to 1. But in the next line, we do compute the envelope with compression. What I mean by compression essentially is it's a way to apply a kind of nonlinear transformation to our stimulus feature. And the reason we do that, there's 2 reasons. One, because it actually allows us to model human auditory perception. So we know from a lot of psychoacoustic studies that were done decades ago that audio intensity does not map linearly to our auditory perception. There's a logarithmic relationship. And so because we're using these linear models, these very simple linear encoding models, we can't really capture that non-linearity from signal to perception. And so a way to enhance these very simple and intuitive models is to apply some kind of nonlinear transformation before we compute the linear model. And so here what we've done is we have raised the envelope to the power of 0.3, which is an approximation basically of that logarithmic relationship that comes from a very old study. And so you can see the effect it has. Basically, it amplifies a lot of the lower intensity parts of the signal. So, the human auditory system has been designed to not just hear the loud parts of speech, but also amplify the quieter parts of speech, obviously to help us understand speech in noisy conditions and whatnot. So you can see the effect of that logarithmic transformation on the intensity, where there's not these huge, massive drops from the louder parts to the quieter parts of the signal. So this will help us, actually compute a better model, a model that can basically achieve a closer mapping between the input and the output. So that's just something I wanted to kind of show you before we continue and demonstrate the feature that we're going to be using as we go forward. So we'll be using this kind of compressed version of the envelope. If you're wondering why the original envelope itself is so small in comparison to the amplitude of the audio signal, it's because, as I mentioned, we use an averaging process. So, you know, to get down from 44.1 kilohertz to 64 kilohertz takes a lot. We have to average across a lot of samples. And, you know, if you are to zoom in on that audio signal, oh my God, this is gonna kill my computer. Anyway, if you were to zoom in on that audio signal, you'd see that it's fluctuating in intensity, you know, from high to low intensity very rapidly, constantly. And if you average across those values, you're not going to get something that kind of traces the very top or crest of the audio signal. It's going to be somewhere in the middle, you know, somewhere between the highest and lowest intensities in that signal. So that's why the envelope looks like that. And something to note that's important, we don't really care what the absolute value is of these features. It's not relevant. As long as we apply these feature extraction methods and transformations in the exact same way across each trial, each participant, etc. You know, we can renormalize these values before we do the modeling itself. So the actual values themselves aren't important. It's more how they fluctuate as a function of time relative to themselves. So does that make sense? Is everything going okay? Just seeing there's a lot of chat going on here. Okay, so did that person find the data stim file? Okay, I think they did. Yeah, and then move it. Thanks, Stephanie. Yeah, to move it to the stimuli folder. Okay, so someone's asking here, how much does the sample rate affect the model accuracy? Well, I mean, if you think about the fact that the first thing we did was low pass filter the EEG below 8 hertz. You know, we're looking at very, very low frequency information here in the EEG signal. We're looking for that, you know, that low frequency information that tracks the speech at a kind of a syllabic or maybe centennial rate. So, you know, if you were to sample your data then at anything higher than 64, like 128, 512, you're not really going to benefit much at all. You might get some nice smoother looking plots is the only thing, but quantitatively, like the type of numbers you'll get in terms of predictions will be very much the same. So you don't need to worry about that. Yes, someone here is just saying that you can also use the Hilbert transform for computing the envelope. That's something we used to do, but the way we're doing it is actually computationally very efficient. It's just a very simple averaging method. We raise the signal to the power of 2. We square, you know, before we average, and then we get the square root again. So it's fairly straightforward. You know, take a look at the MTRF envelope function itself if you're curious to see what's happening under the hood. But basically that's how we do that, and that's the signal, the feature that we're going to work with for the first part of the tutorial. So I'm going to keep going here just in the interest of time. So the first thing we're going to do is run our cross validation. Now, I know I'm kind of jumping straight into a lot of stuff here in terms of, you know, training and testing models and, you know, this is kind of fairly, you know, standard machine learning type terminology, but for some of you it might be new or whatever. So, you know, feel free to stop me at any point and ask. And, you know, you can, it's handy to, you know, put stuff into the chat, but you can also speak over the mic if you want as well, because, you know, I want this to be interactive, and sometimes I don't see what's going into the chat. So just let me know if anything doesn't make sense. So when I say cross-validation, basically what we're going to do is we're going to train our model on a subset of our data, and we're going to validate it on a smaller subset of the data. And then we're going to essentially iterate through each subset of data. You know, that's why it's called cross-validation. We're going to loop through multiple subsets of the data so that every part of our data has been tested on, but trained on a separate subset of data. So what that allows us to do is to tune certain parameters that we need to essentially estimate in order to make sure that we don't overfit to the data. So if we were to take our data and train our model and not check that, essentially, if we were to give it new data, that it performed equally as well as it did on the data we trained on, the data or the model will become what's known as overfit to those data. So there's a lot of noise in EEG. So, you know, there's a lot of stuff you can overfit to there, and we have to mitigate overfitting as much as possible. So that's why we'll cross-validate over a number of different parameters to ensure that we don't overfit. So the first thing, so I'll explain more about what we're actually tuning when we get to it, but the first thing we do here is we apply the compression I was talking about earlier to our envelopes. So the envelopes are contained, as I said, in the first row of our stimulus array. So we can apply that transformation to all of them in one line of code using the cell function again. Next, we're going to define our training and test sets. So as I mentioned, there's 20 trials of data. We're going to allocate our test trials as trials 10 to 13, okay? So that's approximately 20% of our data. So I've arbitrarily chosen our test data to be trials 10 to 13. Oh, after deleting that by accident. Why? Well, you know, you could essentially assign any of the trials as your test data. The reason I picked 10 to 13 was because they're somewhere in the middle of the data set. So, you know, if I was to pick the data at the end, there's the chance that the participant will be very fatigued. And if I picked the data at the beginning, maybe the EEG signals wouldn't have settled as well. So, you know, I'm trying to kind of minimize the risk that the test data is a bad data set. And so I've just chosen these trials in an a priori way. You don't want to go picking them afterwards, you know, and try, okay, well, how does my test results look if I now change my test trials to, you know, trials 12 to 15? That's not what you want to do, because then you're kind of cherry picking, you're biasing your data and your results. So come up with a logical reason as to why they're going to be your test data and stick with that, and don't look anywhere else. Okay. To make it, like, because, you know, this is a data set that was collected elsewhere that we're reanalyzing. There's no data that was officially allocated as test data, so we're allocating the data as test data. I would always recommend, if you're collecting your own data, set aside a part of your experiment as the test data and say, okay, we're officially collecting our test data now, and that's that. And they're kept completely separate then from the other data. That's the safest way to do it. and the least biased way to do it. So anyway, I won't belabor the point anymore, but that's what we're doing here. We're assigning trials 10 to 13 as our test trials. So then what we do is we take just a very easy way then to kind of assign your training and test data is if we create a new variable, EEG train, and equate that to our EEG data, and then from those data we actually remove the test trials. We now have our training data, and then we can assign the test data by indexing those test trials. Okay, so does that make sense? So the next thing we need to do is define our model hyperparameters. So this is the first part of the code that I want you guys to work on. So there's a few different parameters we need to define here. We need to define which channel we are going to essentially base our analysis on. You know, you could pick a range of channels. You could do the analysis on all the channels and then somehow try and consolidate it, or you could pick one important channel like FZ, which is what I've recommended here at the top of the head. So we'll have to define what FZ is. If you go to your EEG structure and click on channel locks, if it'll ever open, you should be able to find channel FZ because it has the labels in here. So if you look for FZ in there and then take the corresponding number here, you should be able to input that there. So the next thing you need to do then is define the direction of causality of your model. So basically, again, this could be a new concept to some people, but we are essentially training a forward encoding model. A forward encoding model is a model that maps from your stimulus to your EEG data. So it follows the natural flow of the data, the causal flow of the data. Okay, the stimulus happens, it enters the auditory system, it's reflected in the EEG. That's, you know, the natural occurring sequence of events. But we can also map in the backward direction, even though it didn't happen that way. We can pretend it did, you know, and use those backward models to reconstruct stimulus features or infer them from the EEG. But here we're building a forward encoding model, so we have to set the direction to either 1 or -1 depending on which direction we're going. Then we have to set the amount of time lags that our model is going to use. So Tmin and Tmax. Basically, if any of you are familiar with ERP type analyses, then you know you'll be familiar with looking at the time course of an EEG response. You know, like in the temporal domain, you typically have about what 300 or 400 milliseconds worth of information in response to a discrete stimulus. So, you know, using that information, that knowledge, that can kind of help us say, okay, we should have a window of about, you know, 300 milliseconds or so in order to get a model that captures all of the processing that occurs in response to the input stimulus. Something we can also do is, you know, your minimum time lag doesn't necessarily have to be 0 or even a positive number. It can be a negative number if you want to include some pre-stimulus information. Sometimes it's nice to do that, particularly for visualizing the response function, so that you can see nothing was happening up until time 0, and then we have, you know, this series of events that occur. And then your Tmax will define, you know, the latest time lag that you'll go up to. Lambda. So then this is the parameter really that we're trying to tune okay, that we want to get right. So basically, you might have heard Liberty talking about the different types of, methods for doing your linear regression, and she mentioned ridge regression. So essentially, we're going to use ridge regression, okay, which involves this regularization parameter. And so it kind of serves two purposes. One, it helps stabilize the inversion of a matrix. But for us, what we care about is the fact that depending on how large we make this parameter, it actually helps us to reduce overfitting of our model. Okay, so if we make it larger, it enforces more smoothing on our coefficients. So, eventually it will smooth them out to nothing, out to zero. But if we get that parameter right, it will give us the right amount of smoothing that it will, reduce the amount of variance in our estimate, and it won't overfit to any high frequency noise, and the model will generalize well to new data. So that's what we're trying to achieve here. So this is basically the parameter that we're trying to tune. So normally when we're doing this, instead of just using a series of like linearly spaced numbers, we might we might space them out logarithmically or something like that. So here what I'm doing is I'm just taking whatever vector of numbers I choose and raising 10 to the power of those numbers. Okay, so you guys can try whatever you think, maybe 1 to 5 or something like that, and see what that gets you, and then play around with it, see if you can kind of refine that down to a better set of numbers. I'm just going to see what I use here, just so I can even give you kind of ballpark. Yeah, you can start with that if you want. It won't put you too wrong. So yeah, basically those parameters will have to be set, and then you'll have to run the cross validation using a function in the MTRF toolbox called MTRF crossval. So if you go to help MTRF crossval, it will explain basically the basics of how the function works, but more importantly, in the meantime, for the purposes of this tutorial, it'll tell you what each of the input arguments mean, and you can just put them in, run the code, and see if it gives you something that makes sense. So while you guys are filling out that bit of the code, I'm just going to go through some of the comments here. I see most of them are being taken care of. So I see someone else asking about another way to extract the envelope using envelope comp. I'm not sure what that is. Is that some standard MATLAB function or something from a different toolbox? I haven't heard of that one. But oftentimes I wouldn't actually overthink really, how you compute the envelope. You could use a Hilbert transform. You could use an averaging approach. Applying the compression transformation makes a bit of a difference, but like after that, you're not really going to see much of a difference, regardless of how you compute it and what your sample rate is or anything. So someone's asking, are the channel location 1020 electrode system? I'm not finding FZ. Oh. Oh, I apologize. Sorry, yeah, FZ won't be there. Okay.
Sorry, can we input just the numbers of the channels, or do we need the names?
Do you know what, FZ, just to, because it's not that important, FZ is channel 85. So if you put in 85 in there, that will that will give you FZ. I forgot that the labels in this particular file are from the biosemi system. So with biosemi, if you get a 128 channel system, it separates the channels into A, B, C, and D. Yeah, it does. I don't know why, but I guess it's just easier to kind of to hook them all up, maybe, or something like that. Oh, sorry, the name of the variable, and I set the compression to 0.3. Thank you for that, Giorgia. Yeah, so the 0.3 compression I used is from a paper. I can link it to you guys if you want. But you know, you can experiment with that number yourself. There's actually a nice what's going on here? God, this thing is so slow. There's a nice paper that looked at a lot of different methods for extracting the envelope. It was kind of more in the context of auditory attention decoding, but it's, you know, it's the same kind of stuff, linear decoding models, and they kind of have a nice summary of all the different ways you can extract the envelope. Okay, so I'm just going to put this into the chat. So that's a paper called, I can't see that, Auditory Inspired Speech Envelope Extraction Methods for Improved EEG Based Auditory Attention Decoding in a Cocktail Party Scenario. So it might interest you guys. Now, how's everyone getting on with the code? Are they getting the cross validation to run? Has anyone actually done it yet? We can spend a bit of time on this because a lot of the code is going to be very similar from there on. You're just going to be working with different features. Okay, so once you crack, you know, it's really important to get this particular part of the code right. Once you crack this, it'll make it easier for you to do a lot of the other exercises, and you'll be able to kind of copy and paste some of what you've done and then make some edits to it. I might as well also just kind of while you're working on that, maybe explain a little bit more about what's happening here. So I mentioned to you guys earlier about this paper that you might find useful. So this is the paper that a few of us put together after last year's workshop. So it kind of goes through like everything, you know, in terms of how to set up your experiment, how to analyze the data, what kind of features to pick. So you might recognize this figure from earlier. So basically, as I was mentioning earlier, we're dealing with a forward encoding model here, okay? So you can see here, forward encoding model, TRF. So because, as I said, we're trying to map in the natural direction that the data occurred in, this model is neurophysiologically relevant. Okay, so the coefficients of our model at every channel, which is what you're seeing here, should look like a neural response essentially. if they're doing a good job at predicting new data, then they'll probably look like an ERP to some degree. Okay, so you'll see kind of some of the typical components that you'd see in an auditory ERP, an AP, if everything is working correctly. Then if you want to map in the reverse direction backwards to create one of these backward decoding models, you might get some very interesting looking topographies, but they're not actually neurophysiologically relevant, okay? Because all you're doing is optimizing the weighting of each channel in order to maximize the correlation or minimize the error between the prediction and the ground truth. So what you see here is something that looks quite different, okay? But as Liberty was alluding to, you know, they have kind of complementary functions. This can be used to do kind of more, you know, qualitative and investigative neurophysiological research in order to understand, you know, the underlying neural process of some stimulus or condition or disease, whereas this is kind of, it can be more useful in an engineering context if you're trying to maybe, you know, build like a real-time decoder or brain-computer interface or something like that. So you can do, you know, all of this just by setting the parameters a certain way with the same code, the same toolbox. So I know we've been here now already an hour. So if anybody is, you know, needs a break or whatever, just let me know. Maybe we could do a break in about 20 minutes or so. Well, I think we're going until 8 p.m. Irish time, so there's another hour left. So it's another kind of useful figure here that kind of just demonstrates the different type of features that you can extract from a speech signal. So we're working with the envelope at the moment, but I'll be showing you guys later how to work with spectrograms and phonetic features as well. And then, you know, they'll have very different looking representations in the brain. So that's still to come. So how can we access all the codes of the session? So I assume you're talking about the solutions, is that right? To the exercises you're trying to do. And they're contained in the folder in another file that has solutions. And to the end, I'd love for you guys to try and do it without looking at the solutions first. Just, you know, have a crack at it as best you can, and I'll fill this out then as we go. So has everyone got it to work, or where exactly are we? Okay, so you're asking about the correlation. Okay, that's a very good question. So you should be aiming for something in around 0.07. I just know that from doing the tutorial myself. That might seem very low. For forward mapping, it's actually not. For forward mapping EEG, it's not, because we've got a lot of noise in the signal to contend with. So if we had lovely ECOG data like Liberty has, we might see much higher correlations, but we don't. There's, you know, even after we've learned how, you know, certain fluctuations in the input map to the output, we're now giving it new data with all this noise that it's never seen before. It just has to contend with that, and it might produce a really, really good estimation of what the neural response should look like, but we can't account for the noise in the actual data we're comparing it to. And so that's just, again, you know, we're trying to help ourselves a little bit by filtering out as much of that high frequency noise as we can. That's why we use these 8 hertz slow pass filters. But anyway, let's just start filling in some of the code here. So we said we're going to use channel 85. I need to uncomment these. We're going to set the direction. Can you explain again how to determine the lambda values, please? Sorry, did somebody say something?
The direction is 1, right?
Yes, the direction is 1 because we're going in the forward direction. If we're doing a backward model, we'd go -1. Okay, so that's explained in the help file in MTRS Crosse file. Maybe what I'll do is maybe I'll move this up here and leave that down there so we can actually see stuff. So if you see in the help file here, it tells you pass in 1 for deer to validate a forward model, -1 to validate a backward model. Okay. So our T-min, we're going to go with -100 milliseconds. Could be anything, but we'll just do it so that we can see a little bit of that pre-stimulus baseline, and hopefully it'll be nice and flat. If we've done everything correct, it should be. If it's not, maybe something's wrong. And for Tmax, I'm going to set that to 350 milliseconds. Okay, so it's the typical kind of window you might use if you were plotting an ERP. You might go out a little bit further for an ERP, but that's what we're gonna use for this, you know, and it makes sense. These parameters are also in milliseconds, and it says that, I think here, Tmin and Tmax are scalars specifying the minimum and maximum time lags in milliseconds. Okay, and then for lambda, we're going to set that to a range of values -4 to 10 and in increments of 2. Okay, so we'll raise 10 to the power of this vector essentially. Okay, and we'll test each of those numbers. Now, I saw somebody said, can you explain again how you determine the lambda values, please? That's a great question. And that's exactly what we're actually doing here. The whole purpose of what we're doing is to actually figure out what should lambda be. So that's why I've used a range of values. Okay, we don't actually know what lambda should be. We don't know what the best lambda is. So I know then you can kind of think, well, where do I even start? And you know, that can be tricky because depending on how your data is normalized or scaled, there's a whole range of things that could affect what numbers should go in there. So unfortunately, sometimes you might have to just use a really broad range of values and then maybe bring it in and kind of fine tune it a bit more. But that's kind of one of the things you'll, I suppose, begin to have a bit more intuition about when you start doing this more frequently, and you know, okay, I've normalized my data in this way, or it's scaled according to this method because I used this system or whatever, this recording system. And so you might know then, okay, this range should capture the kind of, you know, my local minimum that I'm trying to find here. So, okay, we've put in our parameters, our hyperparameters. Now we need to put in, gonna paste this in here. Oh, this is really slow. So I'm going to call this, sorry about this now, it's really slow and jumpy here. So we're going to create a variable called CV. So I should have actually mentioned that because you need to set it to CV in order for the rest of this to work. So CV for cross-validation, we're just creating a variable CV that's going to contain essentially all of our cross-validation parameters. So it'll contain, you know, the OR values, the error values, things like that. If you see down here, we're going to plot cv.or, which is our correlation values, and cv.error, which is our error values. So in place of these guys, we're going to put in our training data, our stim train, our EEG train, and then we can take our sample rate from one of those structures. And we've set dir tmin, tmax, and then our lambda vals. Okay, does that make sense to everybody, what I've done there? We've defined these parameters up here. We're putting them in the order that the function takes them in. And we're putting in our training data. And it's very important that we're putting our training data in. We're not going to put in, you know, envelopes or EEG.data, because that contains all of our data. We just want the training data, and we're holding aside some of our test data for later. Okay. So once that's in, we can run that. And what you'll see now is we're training on 15 folds, we're validating on 1 fold, okay? And it's iterating through each of the 15 folds. So every fold or trial, whatever way you want to look at the data, becomes the validation fold, okay? So first what it does is it computes the covariance matrices, which is basically how we compute our linear regression in a closed form solution, and then it does the training validation after that. So this is the results. This is what you guys should see if you put in the same values for the parameters as I did. This is what you should get out. So you've got the accuracy as a function of your regularization or your lambda, and you've got your error as a function of your regularization. Okay, so what you can see is these lower regularization values tend to be better than the higher ones, okay, because the correlation drops. It goes from about 0.08 down to about 0.06. Same with the error. The error gets bigger the higher the regularization value. Okay, so the more smoothing we enforce, the worse it's doing. So okay, so if everyone has that working, I don't see any issues in the chat so far, and you know, feel free to just turn on your mic and speak up at any point. We'll move on to the next part. Okay, so the next thing we're going to do is we are cool. Yeah, I hope everyone's plots are coming out okay. The next thing we're going to do is we are going to train our final model using the lambda value that we have now determined as being the best one. So whatever lambda value gave us the highest correlation or the lowest error, that's the lambda value we're going to use. Okay. So the first thing I want you guys to do is to get the optimal hyperparameters. So you know that your OR values are contained within cv.or. Okay, so from cv.or you can infer which is the best lambda. And basically how you would do that is you would look at the index of the max value. Okay, so if you guys want to try and grab the index of the maximum value from cv.or, that will tell you which is the best lambda, and then you can train your model here using the mtrf train function. So to do that, you will use mtrf train. So mtrf train, it doesn't do this kind of, you know, cross validation, this iterative kind of chunking of your data. It just basically takes in, if you give it, you know, 20 trials, it's just going to train one model on all those 20 trials. But it works very similarly to the cross validation function. It's got pretty much the same kind of parameters go into it. So it should be easy to figure that out. Thanks for that, Stephanie. Yeah, if anyone is kind of struggling to get parts of the code working, or they feel like they're being left behind, feel free to message like publicly in the chat, or someone directly, either Stephanie or Giorgia or myself. So don't be afraid. Please don't be afraid to ask any question. You know, I still remember when I was learning all of this for the first time, and Ed gave me his code, and I didn't know what was going on. So it's taken me a while to figure all this out as well. So I'm gonna show you guys how to get the oh wait, up here, how to get the best lambda value. So basically, hopefully you guys are familiar with the max function. So or max, okay, so we're going to take the max. We're also going to take the mean, because we have a lot of channels, of cv.or. Okay. So basically, we're taking anything out there. So size cv.or. So just so we can understand basically the dimensions of this. So we've got 16 by 8 by 128. So basically, we've got 16 trials, because we did our cross validation on 16 of them, and we're taking the mean across those 16 trials. 8. I'm trying to remember what 8 represents. I know we have 128 EEG channels. Sorry, 8 is the number of lambda values we have. So that's the important dimension that we're trying to index. We want to know, out of those 8 lambda values that we tried, which is the best one. Okay, so we're taking the mean across the trials. Okay, so we're just going to assume, that there was consistency across those folds, and that taking the mean is the best way to get the optimal lambda. We've only got one channel, so essentially, that'll just give us a vector. Okay, so what we can do with the max function is we can also output the index. Okay, so it won't just give us the max or value, but it'll tell us where the max or value lives. Okay, so essentially, which is the best lambda. And then what we can do is we can set a new variable called lambda equal to lambda vals index. Okay, so that will index our best lambda value. So next up, we're going to train our model. We're going too far. Okay, so MTRF train. So here I've called this E-model. Okay, the reason I've called it E-model is because we're using the envelope here, and we're going to, you know, create a series of different models. So just to be able to distinguish between them, we're going to call that E-model. Same as before. We are going to, I'm just going to take these straight out of here. We're going to use our training, stimulus response, same direction, same time lags, lambda. We've created that variable up here. We don't want a vector of lambdas now, we just want one lambda. The train function only takes one lambda in. It's not going to validate across a series of lambdas. So this is hopefully the best lambda and will give us a really nice looking model that will, you know, predict all the data in the world that we give it. So I'm going to run this now, control enter. So we've created, trained our new model, and this is what it looks like. Okay, so that looks pretty good to me. For anyone who's used to looking at AEPs, auditory evoked potentials, we've got a kind of a negative 100 millisecond component and then 100 type component. We've got a P200 type component. Okay. Sometimes if we were to do this, maybe by including some higher frequencies and not filter below 8 Hertz, we might also see the P1 component as well, but we've done probably a bit too much filtering for that. So you can see here in the global field power as well, those two dominant components stick out, and you know, there's pretty much nothing happening before 0. So if anyone hasn't come across global field power before, it's basically just the standard deviation across all channels. So it's a way of kind of just collapsing across all your channels and saying, hey, when essentially does something happen in my data? Okay, I don't care about the where, what channel. I just want to know, is there bumps in the right places from a temporal point of view? So, you know, we can very clearly see that we've got the two dominant components that we'd expect to see from an auditory response. This is a topography of each of them. So you can see at around 78 milliseconds, we can see our negative component with a kind of a, you know, front of central topography. That's because of the way we've referenced, you know, to the mastoids. Same with the later positive component. It's a little more frontal, which is typical of the kind of time course of auditory processing. So what we've done here essentially is we've created a model, you know, of how the envelope maps to the EEG data. It looks like a neural response, which is a good thing. Okay, that's kind of, you know, check one. And the next thing we'll want to do is, it looks like a brain, but is it good at predicting brain data? Okay, so, you know, if we were using a backward model, it'd be a little bit harder to interpret these plots. We probably wouldn't even bother because it's not really going to tell us much. Whereas here we can kind of say, okay, we're on the right track here. There's very little signal before 0, after 200 milliseconds, and we've got, you know, two nice looking components where we'd expect to see them. So yeah, that's our model. So now we're going to test that model on the new data that we've held out. Sorry, this is a bit jumpy on me here. So what I want you to do next is to fill out this. It's just one line of code, and you're going to test your model using the MTRF predict function. Okay, so for those of you who haven't used it before, it's just MTRF predict. So it's quite similar to the other functions in terms of how it works, except it just takes in the stimulus, the response, and the model itself. All the like necessary parameters in terms of lags, in terms of sample rate, are contained within the model structure. So we don't need to specify them anymore. And the reason we do that is so that it kind of avoids, you know, the user inputting any parameters incorrectly. Okay, so those parameters are already defined in your model. Just remember, now we're going to put in our test data. Okay, not our training data. Okay, so this is data that our model has never seen. So this is the real test of the model to see, are we actually capturing signal, brain-related signal, and can it deal with new data that it's never seen before. Yeah, in terms of the R max and how that relates then to the error measure. So, you know, typically, I can't remember what the actual error values were. 1.18. Yeah, I mean, like, typically we don't see particularly low errors, you know, and as someone's pointing out here, I think George is pointing out, it can have to do with how we've normalized our data in terms of the data that was trained on, the data that we're testing on, etc. You know, there's ways to kind of optimize the model in terms of minimizing error as opposed to trying to maximize the correlation. But typically we focus more on the correlation measures because they don't really care what the kind of absolute values are that our model outputs. You know, you'll see now actually in the next plot where we plot the prediction against the ground truth, you'll notice that there's quite a difference in terms of the scaling of each of those, which is why, you know, you'll get a high error. But we don't really care about whether or not it's getting the exact same values. We just care about, is it predicting the dynamics of the neural response, you know, like when there's, you know, a loud burst of sound, do we see, you know, that reflected in the EEG, and are we able to predict that based on putting that type of input through the model? So, you know, the correlation is kind of insensitive to the absolute values. So it's more about just looking at, are we predicting the kind of the ongoing dynamics of the signal correctly. So how could you repeat how to repeat topographies were chosen? All right, sorry. So the topographies were chosen very simply by just looking at where we saw these bumps. So I ran, you know, I set those values, hard coded those values in. I said, okay, looks like there's something here at about 80 milliseconds and something here at about 150 milliseconds. So, you know, I found the index for each of those latencies and I just hard coded them in. So, you know, you can kind of look, you know, click on the MATLAB plots actually are quite interactive these days. So, you know, you can click on them and you can get the X value. So it's 78 milliseconds, you know, and then go and look at your time vector and see, okay, what index corresponds to 78 milliseconds. And then you can plot that, or you can just plot loads of top plots and look at how it evolves. And you can even make really nice movies out of them as well. There's a way in MATLAB to actually like create a movie out of a sequence of plots, and you can kind of see the evolution of the signal traveling over the scalp. It's really cool. I'd say if I did that now, my computer would probably explode. So I'll just keep going here. Now, I've got this error message, stim and response arguments must have the same number of observations. Okay, interesting. So that would indicate that the function at the end of your pre-processing chain, for whatever reason, might not have truncated your data correctly. Or else something strange happened, maybe. I can't really see where else that would have happened. Same number of observations. Yeah, so something to do with the number of cells. So did you get that error, Anna? Did you get that error when you tried to run the cross validation? Or was it during model training or model testing? Because it would be unusual if you didn't get it for the first two, but are getting it now when testing the model. Huh. Okay, well, I'll just put in my code here, and you can see if that matches up with what you've done or if you've done anything different. So we're going to call this, what do I? So the output of this. So basically, there's two variables being output from mtref predict. The first is our actual prediction. So it's our estimation of the neural response. Test is just a variable, a structure, I think, containing all of the test statistics. And then we're going to put in our stim test, our EEG test, and our model. So I'm going to run that now and see, does it work? Or do I get an error as well? Okay, I see. So you guys figured it out. Yeah, EEG train, yeah. Okay. My computer's so slow right now, I actually can't even tell if the code is running or not. Jeepers. I never knew Zoom was so computationally heavy. Okay, what's happening there now? Okay, so we've got it. Right. So this is what you should get once you run that code. Basically, I have a plot here of the original, the ground truth, EEG in blue, and our prediction in red. It's kind of hard to appreciate when you're eyeballing it, especially with such a noisy signal. But we can see by looking at the correlation that it didn't do great, if I'm honest. You know, it's about half of what we got from our validation set. So anyway, I'm not going to dwell on that too much. Sometimes it'll be the exact same, sometimes it'll be a bit more. It could have been a little bit lower because of the particular trials we chose. They might have been a little bit noisier. It's hard to know, but anyway, what we're going to do next is we're going to look at more sophisticated features, and you'll see what happens then once we start, using these kind of multivariate features. Okay, so I know we don't have a huge amount of time left, but if people would like to take just maybe 3 or 4 minutes to, I don't know, go to the bathroom or get a drink of water or a cup of tea or something, why don't we just recommence at 7:40, so in 4 minutes. Okay. Okay. Oh, sorry, maybe that person didn't know we were on a break. We just took a little 4-minute break there, just in case anyone needed to go to the bathroom or take a drink.
Yeah, I took a break 30 seconds before you said to take a break, so I came back and I was very confused as well.
Oh, sorry about that.
It's okay.
Bad timing. Yeah, well, obviously it was a good. I probably should have. Sorry, I should have called a break earlier than that. Okay, so I'm gonna try and move along a bit quicker now because we've kind of covered the basics of, you know, how you basically validate, you know, tune your hyperparameters, how you train and test your model. Okay, and now it's just a case of like using different features and data sets, etc. Okay, so the next thing we're going to do is we are going to visualize our spectrogram. So what I want you guys to do is apply compression to the spectrogram. Now that you know how to do that. So that's a fairly simple one-liner. And basically what we're doing is we're kind of now going into what we call multivariate analysis. So instead of just trying to map a one-dimensional feature to the EG, we're going to try and map a two-dimensional feature. So we're going to have both frequency and time that we're mapping to the EG data. So just so you guys know, when you do the compression, I've called that new variable spectrogram comp, okay? So we would so we're going to set that to our spectrogram, and then we're going to raise it to the power of 0.3. Now, an important point to note is that I use a dot here before this character. I don't know what's that character called, hat or something. And basically what that does is it raises every individual sample in that matrix to the power of 0.3. Okay, instead of, you know, doing some sort of matrix multiplication and trying to square the matrix or cube the matrix. Or sorry, it's not even a cube. Okay, so that will apply the compression to the spectrogram, and then if we plot that, we should get a pretty looking plot. Okay, so here is our original audio at 44 kilohertz. Here's our spectrogram at 64 hertz. Okay, so like what Liberty was showing us earlier with that amazing kind of interactive web app where you can speak into it and look at the spectrogram of your voice, you can kind of see the frequency content here between about 200 and 8,000 hertz. And once we apply the compression, you can see a lot more information kind of in between the peaks. So it's not just this kind of sparse looking spectrogram, it's kind of amplified or emphasized a lot of the lower intensity frequencies and time points. So this is basically the signal, the feature that we're now going to work with to create our model with. So we're going to do the same again. We are going to set our hyperparameters and do a cross validation. I'm going to pick the same channel. We're going to map in the same direction. We'll go with the same time lags. C2. So 350 milliseconds again. We'll go from -4 to 10. So I'm not changing anything here, okay? And then let's run our cross validation. I'll go up here. I'm gonna copy that same line of code. So is there anything I needed to change? No. So we're basically overriding, you know, any of the previous variables again, but we're setting them all in the same way. You know, we're defining our test and training sets in the same way, using 20% of our data, the same trials, removing them from the training data. So it's pretty much the exact same code. We've just defined, you know, like here, stim train as spectrograms instead of envelopes. Oh, I need to also apply compression to the spectrogram. Why don't we just do that again? Oh yeah, so this time it's going to be a little bit trickier, okay, because we have more of them. So spectrograms. So we're going to use the cell function again. Okay. And what we're going to do is we're going to take x, we're going to raise it to the power of 0.3 like before, and x is going to be our stim.data, and this time it's going to be the second row, which is the second row in our cell array, which is the spectrograms. Remember, the first row was our envelopes, second one was spectrograms, third was phonemes, fourth was the semantic dissimilarity vectors. And then we need to also put in uniform output to false. Okay. So that should work. That should apply the compression to every single spectrogram we have in all of the cells. And then we're assigning our stim train to those spectrograms. And that's pretty much the only difference. This line here and this line here, the only difference is really then here where we set the test data compared to the first cross validation we did in B2. So I'm going to run that now. If you don't get any errors. Oh, great, I got an error. No, I spelled uniform output wrong. There we go. Uniforma. Okay, now it's running. So again, we're training on 15 folds, we're validating on 1 fold, computing our covariance matrices, and now we're training and validating our model. And just to give another little bit of insight into how this works, so I mentioned earlier about the covariance matrices that we compute for each fold or each trial. Basically, what we do is we compute them separately for every fold. And then in order to consolidate all of the training trials, we can sum across all 15 covariance matrices. And so a computationally efficient way to do that is to sum across all 16 of them at the beginning, and then to just subtract out each one as you iterate through your folds, instead of doing the summing of 15 on every fold. So that's just a kind of a little insight into how this works to make the training process faster. Okay, so we're seeing kind of a little bit of an improvement, I'd say, in our validation accuracy. We're getting up to about 0.09. Exciting stuff here. So it would suggest that maybe the spectrogram model is working a bit better. So let's take a look at our model. So again, we're going to get the best lambda values in the same way. Nothing different from the last time. For max index. So we're going to take the max of the mean across trials, cv.or. You could, you could equally do the same thing and take the min of the error, but because the correlation is the metric that we're more interested in, we're going to take the max correlation. And then we'll just specify which channel we're going to base it on. Wow, the new MATLAB is quite different. It preempts all sorts of things you could possibly write. Now, and then we're going to train the model. So again, that's going to be the exact same as last time. We go up here to where we trained our envelope model. We're now going to train our spectrogram model, which, what do I call that? S model. Simple enough. Okay. So I'm going to run that now and train our final model using the optimal lambda value. Oh, I didn't redefine lambda though, did I? So I should have here. So actually, it might be good to actually look at this and see what it gave me out. So this is what it gave me using the wrong lambda value. So not the worst looking topographies, I'd say, but certainly when we look at the time course as a function of frequency, it kind of looks very noisy. It doesn't really look like a brain signal. Okay, that's because I chose the wrong lambda. Maybe I did it on purpose to show a lesson. And then down here we should have said lambda equals lambda vals x. Okay, so I'm going to run that again. So hopefully we'll get a much nicer looking model this time. Okay, much better. So now taking the topography at the exact same time points, we're seeing a negative component, we're seeing a positive component. And we can really see these now, these components as a function of frequency. And you can see that, the time course of these components is a little different depending on what frequency range you consider. They're a little earlier in the higher frequency range and a little later in the lower frequency range. Okay, but basically this is how the spectrogram maps to the EEG. And so we can use that model in the exact same way as an envelope model to predict the neural response. So I'm going to do that now. I'm not going to wait around too much longer because I know we're coming towards the end and I want to get onto the decoding model very briefly. So test that. And why didn't that work? Oh yeah, E model. We need the S model because the E model no longer has the right dimensions to deal with the test data, because we've redefined our test data based on the spectrogram. Okay, so when we run that with the spectrogram model, this is what we get. So I think we did a bit better, a good bit better on the test data this time with the spectrogram model. So I know we've gone through a lot now, and you know there's a lot to take in and stuff, but I'm going to jump from there to the decoding stuff. If you guys want to work on the other exercises in your own time, there's the very same thing, only using phonetic features. So if I run the next guy, you can see here, these are the phonetic features. So similar to what Liberty was explaining earlier, you know, you've got all these different types of sounds, plosive, fricatives, and you know, we've basically mapped out where and when all of these phonemes occur across the time course of the stimulus. And so we can input this essentially binary matrix into the MTRF toolbox in the exact same way as a continuous variable, and it'll work just the same. So you can work on that exercise yourself, because again, it's just a case of, you know, putting in the parameters, running the code for the cross validation, training the model, testing the model. You have the code now, and it's also in the solutions as well, so there's nothing new there. And then after that, then there's the semantic vectors, which we can visualize as well. So basically, this is what we call semantic dissimilarity. So this is the onset of each word, okay? And basically what this tells you, this the value here tells you how dissimilar that word was to every other word in a sentence, okay? This was kind of inspired by the N400 work that some of you might be familiar with by Kutis. So it was kind of this idea that we can extract an N400 type response from naturalistic stimuli by just indexing where essentially each word occurs and how similar or dissimilar it is to the surrounding words within the context of the sentence. So yeah, feel free to work on that exercise as well. Again, there's nothing new there really. It's just a new stimulus feature you're working with. It's all the same code again. So very quickly, I know we don't have a lot of time left, but again, if you go to MTRF tutorial part 2, we can very quickly just do the decoding analysis. So really, there's not going to be a whole lot of difference here. The main difference is that, you know, we specify that we want to map in the opposite direction, okay? And we might set some of the parameters a little bit different in terms of the pre-processing. I'm going to pre-process the data in the exact same way. I'm not going to change any of those parameters, so it's all the same as before. I could have even just run this code here without reloading and pre-processing the data, but anyway. So the first thing we'll do is, yeah, we can visualize the envelope if we want, but sure, we've already done that. So we'll move straight down here. Okay, so the first important thing we have to do here is we have to specify our direction as -1. Tmin might go with 0 this time, because we're not going to actually visualize the decoder weights in the same way, because the time course isn't as interesting to us. And we'll set this to maybe 250 or 300. Let's see what I set it to before. So because we're mapping backwards, we have to map basically 128 channels back to the envelope. There's far more features that we have to map onto the output. So it takes a lot longer, the backward analysis. So I'm trying to kind of minimize the amount of time lags that I'm using here to make it as efficient as possible without kind of sacrificing the accuracy of the model itself. Okay, this is very slow now. I think it's just about done pre-processing the data. I hope no one else is this slow. Okay, so I was just checking to see here what's a good range of lambda to use. So in the solutions, this is the range of lambda that I use, just in the interest of time. So it's a little bit different. In fact, really all I've done is actually use the smaller range of lambda, just probably to speed up the analysis. But again, you know, if you didn't really have a good starting point, you might have to use a broader range and then kind of figure it out by trial and error. But we're doing it in the same way. We're just raising 10 to the power of this vector of numbers here. I'm going to try each of those incrementally. Then we are going to use the cross validation function in the exact same way as before. No differences here. Apologies now, I know we've gone over time, but I think if we get through this, it will have, you know, you'll pretty much have everything you need then to do any of the other exercises. So stem train, EG train, fire parameter set. Okay, so I'm going to run that. So you'll notice now it's going to take a bit longer to compute our covariance matrices compared to before. Nearly there. Okay. All done. So as you can see, we get much higher accuracy in terms of the correlation values for the decoding models. The reason for this is because one, we're trying to map a lot more features onto the envelope compared to the univariate analysis that we were doing before when we were trying to map just an envelope to one single EEG channel. The other main factor I would say is that we don't have the same noise to contend with. So once we understand the mapping from EEG to envelope, every time we give it a new set of data, when we're computing the correlation between our reconstruction and the ground truth, there's no noise to contend with, okay? So if we do a good job of reconstructing what the envelope should have looked like, then we should get a very high correlation between that and the original. Whereas with in the EEG domain, you have all this noise to contend with, so it doesn't matter how good you do. So anyway, that seems to be working as we'd have expected. We'll quickly just create our model and then test it. So this is literally the exact same code as before. The only thing is here, we don't have to specify a channel because we don't have multiple channels. We just have one feature with the envelope. Now, it would be different if we had like a spectrogram. You might have to specify, okay, a particular frequency band, or maybe average across a certain number of frequency bands of interest. But here we're just giving it the entire matrix because we don't have any other channels. Then we'll create our backward model. Okay, so it's training the model now. While it's doing that, we'll put in the code for testing it. Okay, so we have our backward model. This is what the decoders look like in terms of their topographies. Nothing great to look at. Normally what we see with auditory data is a lot of weighting of the kind of temporal electrodes. This one's a bit strange looking. It kind of looks like it's like the very outermost channels or something like that. So it's done this kind of weird interpolation. But normally you'd see these kind of bilateral weighting in the temporal regions. So we'll test that model now and see how well it works. Okay, so it did pretty good on the test set. So it did a little bit better, in fact, than the validation set. So again, in around the 0.15 correlation mark. So it seems to be working as we'd expect it to. So that's basically, you know, like there's no point in me kind of going through all the other stimulus features now. You know, you could take that same code and you could apply it to the spectrogram as well. It gets a little bit tricky when you start trying to use more kind of categorical features like phonemes and semantic vectors for doing backward analysis, because it's harder to you know, actually reconstruct these binary representations and then figure out how to compare them to the original. Sometimes you have to kind of apply some sort of nonlinearity to them afterwards. So we don't tend to do that as often, but you could very easily do with the exact same code, reconstruct the spectrogram and look at how well that model performs. So I'm not going to go through that, but the last thing I do want to do is just to run this final block here to do the single lag stimulus reconstruction. So basically, what this does is, instead of integrating over, say, 250 milliseconds of EEG data, we're going to take each lag separately and do an individual reconstruction for each of those lags, and then plot the correlation as a function of those lags to see what lags contribute most to the predictive power of the model. So, you know, like we can kind of infer that from the forward models to a certain degree. We know that, okay, given that it's got these like dominant components at about 100 and 150 milliseconds, that's the kind of window we should be using. But you can also do this single lag correlation cross-validation analysis to also look at where the kind of most important time lags are. So I'm just going to put for this. So this should run pretty fast because it's not going to integrate over loads of data the way the other one does. -1, we're going to go this time from -250 milliseconds to 500, because we are kind of going to look at this time course. And then for this, what we're going to do is add in one additional argument, if it will let me. Okay, so everything is the same as before in terms of, you know, inputting our training data, sample rate, time lags, lambda, but this time we're going to set the type of analysis to single. Okay, so instead of integrating across those time lags we've given it, it's going to compute them, models for them individually. So we run this, it should be pretty quick. Or not. Okay. We're nearly there, folks. I'm sorry for keeping you guys 15 minutes over. I know this is supposed to end 15 minutes ago, but I just wanted to kind of spend a little bit of time talking about the backward modeling stuff. So this is what we get in the end. Okay, so instead of, you know, looking at the kind of typical bar charts where, you know, we've got our correlation for the validation and test set, now we have this plot of correlation as a function of time lag. Okay, so it just gives us a little more insight into what's happening. Okay, you know, we can see that obviously if we use these negative time lags, nothing happens. It starts to creep up a little before 0, potentially because of the filtering we used. Remember, the filt HT function isn't a causal filter, so, you know, we're filtering forwards and backwards, and there could be a bit of information spread across that 0 boundary. But, you know, certainly once it hits 0, we can see that, okay, the signal is on this side of the 0 time point. You know, we can see almost like before these kind of dominant components, and at about 80 and 150. And there's a little bit of stuff here happening in around 400 milliseconds, which I don't know if that's related to the N400 stuff we were talking about earlier. But if you do run the semantic the similarity exercise, you should see an N400 component in the data. But anyway, that's basically it. If anybody has questions, feel free to throw them into the chat there now, or just talk over the Zoom chat.